In this video, we're going to take a look at the concept of equilibrium. So this is an introduction to chemical and physical equilibrium. In fact, equilibria of all types. So far in your chemistry journey, you've studied reactions that have gone to what's called completion. So in other words, you would see a reaction, for example, like Na and Cl2 reacting, and that'll produce NaCl. And so when we say gone to completion, essentially that means that it all goes from the left to the right, and that's the end of the story. All your reactants are converted to products. Now, in reality, that's not really the case. There are a lot of reactions that actually do not go to completion. Instead, they're actually reversible. They go both ways. They go from left to right, this way, and then from right to left, this way over here. So we call those reversible reactions. So the whole concept of the equilibrium unit is going to be to study reactions that are now going both ways, left to right and right to left. And the idea is that your reactants are converted to products, and then as your products build up, those products themselves start to react and then reform the reactants back and forth, back and forth, back and forth. So when we talk about reversible reactions, we say that there's a forward reaction, and the forward reaction is the one that goes left to right. So you read it from left to right. And then there's a reverse reaction. That's the one you read from right to left, so going this way. And to represent that, we use the double arrow system, the double arrow. So completion would be a single arrow like you're used to using. And a lot of the reactions that you've studied, they might have gone to completion, but for the most part, they exist in this double arrow system, this reversible reaction system. So to truly represent them, you have to have a double arrow, one arrow sort of pointing towards the right side, one arrow pointing towards the left side. So in your system, if it's closed, what's going to happen in these sort of reversible situations is that your reversible reaction will reach what's called an equilibrium. So far, the general idea is that, a lot of the reactions you've studied have been completion reactions. However, many reactions do not go to completion. They are reversible. They go both left to right and right to left. To represent that, we put the double arrow. Now, if you're in a closed system, that reversible reaction is going to reach what's called equilibrium. And I'm going to try to explain that concept using the graph over here. So this graph actually represents the equation we had above. It has N2, that's in its gas state, plus 3H2. And it's going to go reversible here. So we'll have 2 NH3 produced, and then at some point, the NH3, as it's being produced, it'll re-react and reform the reactants. But let's look at a graph and see what's happening. So this is our concentration over here, and this is our time. And you'll notice if you look at the N2 and the H2, at the very beginning of our reaction, that's all we have present in our flask, in our beaker. So pretend there's a beaker here. At the very start, you just have N2 and H2. And your product, NH3, has not been formed yet. That's the beginning here, time 0. But over time, as time goes by, your N2 starts to drop. Or that's your H2, sorry. And your N2 does the same because you're essentially using up the reactants to make product. So your NH3 starts to rise. And you'll see that it's actually a pretty fast decline at the beginning, pretty fast increase at the beginning. But eventually the decline and the increase, they start to level off. And so what you'll see is that there's a point where you no longer have a change in the concentrations. So as soon as we kind of reach this dotted line here, the concentration of the reactants and the concentration of the products have stopped changing. They flatlined. So what's essentially happening is at the beginning, you have a lot of reactant being converted to product because that's all you have, all reactant, and no product. And slowly, as the product starts to build, it will start to re-break down into the reactant. And it'll pick up speed as more product is made. But the idea is that eventually, both these processes going left to right and right to left, they'll start to happen at the same rate. So at first, it's your reactants being used up that's faster. And then your products being used up starts to slowly pick up. But there'll be a point where that going this way, left to right and right to left, reaches the same rate. The speed at which these are used up will match the speed at which this is used up, the product. And that's shown by a flat line of all your involved components, reactants, and products on the graph. It's at that point that you reached equilibrium. So how do you know you've reached equilibrium? Your concentrations of everything stops changing. And that's because the rate of the forward is now the same as the rate of the reverse. It doesn't mean that the reaction is stopped. The forward is still happening, and so is the reverse. It's just that they're happening at the same rate, so it looks like nothing is happening on the outside, but in reality, they are going back and forth at the same rate. So, what is equilibrium really? It's the state of reaction in which the rate of the forward reaction and the reverse reaction are equal. And we know you've reached equilibrium when the concentrations of the reactants and products stop changing. Again, it doesn't mean that the particles have stopped moving and the reaction has stopped altogether. It's still all happening. But the rate at which it happens going reverse and forward is the same, so it looks like nothing is happening. These concentrations are no longer changing. So basically, like as soon as this is used up, this is broken back into that. So it looks like nothing happened, even though something did happen. It's almost like if I was on a bus and the bus drops one person off at the bus stop and one person gets on. There was definitely movement. One person got off and one person got on. But it looks like on a whole, nothing happened just because you lost one person, you gained one person. And they kind of got on and off at the same rate. You didn't even notice. So that is what a chemical equilibrium is. And as long as you're in a closed system, if you have a reversible reaction with those double arrows there, that system should reach equilibrium at some point. So you're going to have that decline of reactant at first, that increase of product at first, but then eventually that concentration flatlines. And so when that concentration stops changing, that's when you know you've now reached the point of equilibrium. So in the next segment of this video, we're going to take a look at equilibrium graphs in a bit more detail.